So today's topic will be prefix complexity, and we have three theorems, but two last theorems will be a bit easier. So I think it's not theory lecture will be easy, and there are not too many exercises. I printed them, and hopefully I was clever enough to bring them. Yes. Yeah, so next lecture we will discuss application, and there we only need one theorem, and then there is some blah blah. And I will not have seminar because it's too hard to invent exercises and maybe not necessary. So I will just speak about some discovery of 2004, about some machine learning algorithm. At the time, they were the best algorithm, and the idea came from Kolmogorov complexity. So it was basically about first word embedding. So there is clustering by compression and Google distance, and there was a simple way to compute word embedding. Switch it off. So for today, so previous lecture, we had annoying logarithmic terms each time we wanted to concatenate codes. So we will change the definition of complexity today and to get rid of such terms. And we get more precise versions of many theorems. Moreover, we will prove coding theorem. So I will, with this prefix complexity, we will get a better version of symmetry of information. And we will prove coding theorem that relates probability to Kolmogorov complexity. So remember the first lecture, we spoke about Solvanov induction. Then we started new topic about like more combinatorial topic. And thanks to coding theorem, we will see that a priori probability of finite string is the same as prefix-free Kolmogorov complexity. But a priori probability will be slightly different definition for we will consider measures over strings, finite objects, not infinite sequences. For infinite sequences, the connection is there is some small technical term that appears, and all proofs. Actually, this term is not yet understood. So there is open question and things are pretty difficult. Okay, so let's start. So let's start from beginning again about a priori probability. So now we will consider any probabilistic machine that has zero input and prints out strings. So our machine will be, let's call it V. So V, no input, and it produces a string. So when we say V produces a string, then it has an output tape. It prints the bits, and then it halts. And when it halts, we understand that it's finished creating the output. So that's different. Before we had machines, we could, they were useful even if they never halt, because they can print infinite sequences. Now we want machines that print finite sequence and halt. And I will not bother about the input. So machine can ask for random coin. It has a coin, it can flip the random coin if it needs randomness. And so it creates a distribution over a probabilistic, not distribution, but semi-measure over strings. So let us, okay, let's write it, no input, and then output equals string after halting. And so the structure of the lecture, it follows chapter 3 in Shen-Uspensky-Vereshchagin book. They also start like this. I think it's nice to start like this. And now we can define some measure over string. So it will map as before to numbers 0 and 1. And we say that or the measure is just equal to the probability over random coin flips of the machine that V outputs. Sorry, I should probably write bigger for people. So there are some online people. Yeah, but the quality of the image is good today. But anyway, I will write a bit bigger. Output V outputs. So if we have probability, so we have a measure, and so what we know is that sum of PV over all x over the finite strings is some number smaller than 1. And so machine might never halt with certain probability. That's why we don't have equality to 1. So we just have inequality. So, but I will still call it semi-measure. But now it's discrete semi-measure. So there is only one condition. The sum is at most 1. Okay. And so now again, there exists a machine for which this semi-measure is bigger than for all other machines. So can you guess why there exists such a machine? So you have random coin flips available. Yeah, repeat the question. Okay, yeah. So we again have a notion of domination. So let us say that PU is bigger up to constant factor than PV. So this definition, if there exists a constant for all strings x, we have PU of x bigger than 1 over constant PV of x. So this definition, PU is larger than PV up to constant factor. And now we have a theorem that says there exists a machine. So there exists U, so that for all V, PU is bigger up to constant than PV. And so now my question, construct such a U. So what are the actions of the machines? It just can ask, it's a Turing machine. So it has certain state, and if it goes into certain state, then it will receive somewhere on the tape a random bit. And then this probability is defined over receiving random bits and the operation. But we can still do the same thing as before. So it can ask for random bits and then interpret the random bits as a description of another machine, as in prefix-free way. So a task for prefix-free description, code of a description of other machine. And then it simulates this other machine. And each time the other machine asks for random bit, he asks the oracle for his random bit and transfers it. And so in this way, machine U has a certain probability of simulating any other machine. It was we had a similar proof for continuous measures. So there, but there I made explicit, the randomness I wrote explicitly. But now I thought, okay, maybe it's not needed. Let's skip it. Then all the definitions are a bit easier. Okay, and so now we have a new definition. So people use the letter M, small m, for the discrete a priori probability. And M of X is the probability of PU of X, where U satisfies the condition of this theorem. U as in theorem. So this theorem. So that's it. So this is a priori probability. And almost all observations we had about Solomon induction, they have similar observations and properties for finite strings. So in Solomon induction, we had infinite horizon, and we could speak about infinite prediction. Here it's a little bit difficult. Here we will speak about finite predictions. So we try to predict the next bit, but it is like of our nature suddenly disappears when we predicted the last bit. But we can conditional long enough inputs or something. Okay, so we can also define a notion of conditional a priori measure. Let us do it right. No, let's postpone it a little bit, sorry. Okay, so this is a priori probability. So it's our first definition. Second definition will be prefix-free Kolmogorov complexity. So our first coding theorem will say that minus logarithm of M of X is equal to prefix-free Kolmogorov complexity. That's what we will prove in a second. But first, let us say what is prefix-free complexity. So now we, so before programs were strings, they were given to the Turing machine as a string. That means it appears on the tape followed by blanks. Now we will put an extra requirement on the program. We will only consider machines so that whenever a program halts, it cannot be a prefix of another halting program. So we will consider, so we say that the decompressor is prefix free. If it works, so whenever it works, it does not work on a word that's a prefix. So we have a decompressor 0, 1 star, 2, 0, 1 star. Oh, yeah. Now I need to repeat the definition. Okay, but you're just in time for the second definition. So is a prefix-free decompressor, or yeah. Well, actually, let's use the short name. So when I first learned that, somebody was angry that I said prefix machine instead of prefix-free machine, and I was so impressed. But now it's clear that both are okay. So D as a prefix machine. So if so, D, so that means defined. If I write the arrow, so defined. And Q is prefix. Then EQ is defined. Okay. So now we can define, so when we use prefix machines, we use the letter K for Kolmogorov complex instead of C. So it was not by Kolmogorov. He used, well, I think he didn't publish about prefix Kolmogorov complexity. So it was student Levin from P versus NP problem who started to think about this. So K, but I think he also used other notation. I don't remember. So KD But this is the same definition that we already know from previous lecture. So it is minimum of the length p for which tp equals x. Okay, and now you can guess what is the next step. We need to agree on some decompressor. So we need to fix a special one that for which complexity is shorter than all other decompressors. And so we have similar theorem. So there exists, or I already have a u. Okay, so there exists u prime. Then for every prefix machine v, there exists a constant c for all x, and prefix complexity, let's use d, that's prefix complexity of x is smaller than prefix complexity of u prime is smaller than prefix complexity of 1 plus c. Okay. And before, the proofs were always almost trivial. Why there exists such a u prime? So before, when we proved it for plane complexity, we had just this compiler that we pre-appended to the program. And then we obtained just another decompressor. But now we cannot apply the same trick to construct it. So sorry, there exists prefix free, has to be prefix free. So exists prefix machine u. So there exists prefix machine u prime, so that for every other prefix machine u d, complexity is better up to constant c. Okay, so if we do exactly the same construction as for plane complexity, we run into a problem. Why? I mean, it would be unfair if we use, so now, yeah. So now there is, before we could use any compressor. Now we only use special decompressor. So the Kolmogorov complexity would be larger. But to construct optimal machine, it would be cheating to use the optimal one for plane complexity. Then whatever was it, so I told some motivations why we wanted prefix-free machines that would destroy our motivations when we use a bad u prime. So it needs to be prefix-free. But then just so when u prime uses a compiler, he needs to see that he simulates a machine that's also prefix free. And this is a problem because given a program, you cannot know whether it so that it's even harder than solving the halting problem. Given the description, getting some property from the mapping it computes. I forgot the theorem there, so a general theorem about. Okay, anyway, so we cannot see from the description. So now we need to work harder to obtain an optimal u prime. But it's not so much harder we need to work. So what we will do is we will make a, so what's the plan? We want to simulate any other decompressor, any other plane decompressor. But our optimal machine will monitor what the other compressor is doing. And if it violates this prefix constraint, if it tries to halt on some prefix of a program that it halted previously, it will say, okay, now I stop simulating you. All your programs are undefined from now on. So it kind of freezes the machine. So it will send all the programs in infinite loop. So of course, this is very extremely slow simulation on u prime. Because if you give it a program, what it will do is start simulating all the programs. And each time some program halts, he recorded in a list until he sees that your program that you gave it appears on the list. So this is a very slow simulation, but unfortunately, it's the only way to guarantee that you simulate every other prefix-free decompressor. So when you have a description of a machine that is actually prefix-free decompressor, he will never freeze anything. And so he will just let this decompressor work. So if it receives a compiler of good prefix-free machine, then he will not interfere with its programs. But he will slow down it by a huge amount. There is exponential slowdown. But okay, this theory is not designed to be practical. But of course, you can approximate prefix-free complexity by actual compressors and decompressors. But then you will have a lot of structures you don't need to check anything. Okay, so this for next lecture. So we will speak about some ways to approximate it, and it was successful. Okay. And what else should I say? So do you want me to say the proven details, or it's clear how to do it? So should I write a formal mathematics, or you're convinced that such machine exists?
Like our machine need to understand whether the other machine how.
Yeah, whether this condition is satisfied, that's the problem. And so previous proof, we had plain machine. That means that, okay, so idea is that Turing machine and programming language or decompressor, it's 3 times the same thing. That's the intuition for common Born complex. So you allow to decompress, but have full power of any programming language. And then we claim that we have the best machine. And so if you say, oh, Python is the best language for compression, and somebody else say, no, it's C++, or somebody can come up with another language, then you say, okay, I use C++. I can write compiler for any language you want in C++, and I will prepend the compiler. And length of compiler will be this constant C. And before there was 0 conditions on what decompressor does, so we were done. There was nothing to prove. But now we have a condition here, and we want that our universal decompressor satisfies this condition. So we can only give it compilers that also satisfy the condition, but that doesn't work, this idea. So the second best idea is that whenever it simulates another machine, it will carefully monitor what it's doing on all the programs. And if it sees a violation, then he blocks the machine. He says, no, I'm not gonna halt. No programs for you are halting anymore. And now U prime is on the complete set prefix-free. And why is the reason? Because we use prefix-free descriptions of compilers. So every compiler already has corresponds to its own set or prefix-free set. So if you have 2 sets, so if S1 is a set of prefix strings and S2 is a set of prefix strings, then the set of all concatenations is also prefix-free. So that's the property we're using. So we use prefix-free descriptions of compilers and then ensure that their program, their code words are also prefix-free. And so concatenation of 2 prefix-free sets is also prefix-free set. And so we understand that U prime is prefix-free. You know what? I need to write lecture notes. So I will write about it. But it's also in Shan book. No, but we have time. There is not so much material, so I can say one more time. Let's write a bit of proof.
think that I don't quite understand how we don't put words also.
Because we don't try to look at the code and understand it will do something for all the programs. We just we let some programs through. And so first strategy is look at the code and say, oh, you're bad, you will have no programs. But that's impossible because of halting problems. So we do the second thing. So they say, okay, let's believe you. Like you can assign code words. But whenever you assign a prefix of another code word, you are done. I'm not gonna allow this. So the U program is like supervisor who checks. So when it receives a compiler, he says, now I can check what everything you could possibly do on all the programs. And we could, and so he does a lot of work. And then at some point, he sees that he violates a rule. And then he says, from now on, you stop. But before that moment, he has already let through some programs. So that's how we go around it. We just wait a bit longer. So we're kind of late, well, not lazy because it's a lot of work to do what he does, but so just more trusting. Okay, so now, well, I can write what U is doing in full. So let's make a bit more space. So if U prime gets an input, he will split input in two parts. So he will say, so remember that, well, I'm not so good in remembering faces, so I don't know if you were here or not. But we had this notation that if there is a string, when we put a line over it, we put a 0 before every bit, and in the end, we put a 1. And that's a prefix code. So U prime will check whether there is a 1 in odd position. If there is no 1 in odd position, then it just stops. It doesn't output anything. And otherwise, it can split the input into two parts. So P will be interpreted as description of machine, and then he will run Q on this machine. But he will run in a special way because he will check whether P does not output two programs that has no two code words that are prefix of each other. So it will start by running all programs in parallel and keep a list of all the programs that halt. And then if there is violation, he stops. And when Q appears in the program that halt, then he gives the same output. So that means Q will go through on the condition that machine P did not make a violation before stopping on Q. Okay, so I didn't write anything, but it okay, so if equal to yeah, if we want to machine with description P on Q if no violation on time VQ. So time VQ is the moment that VQ halts, VP of Q halts. otherwise, it's just undefined. Okay, let's continue. So, so now we understand AU prime very well. I mean, I forgot to look to the others too. So yeah. So now we have a definition. Okay. And first theorem is that coding theorem is that two definitions are equal. There is one direction that's easy. For other direction, we need lemma, craft lemma. So let us think what is the easy direction. So let me write it. I didn't tell you the other definition. So a priori probability, we will consider discrete version. So there is a machine V with no input. And machine V outputs a string. That means it prints bits, zeros and ones. And after some time, it halts. And when it halts, we understand what its output. So it's different from previous lecture where it prints infinite strings. Now we care about finite strings. And so we want to define a priori probability. It goes by such machine. And so we can define the probability that V outputs a string. So I will write this by PV of X. That means probability that machine V prints X. So V has access to random bits. So there are coin flips. And before I wrote these random bits explicitly as infinite sequence, now I don't write them. So just assume machine has special state to flip a coin. Okay. So this probability goes over the random coin flips that it asks about. And so we get the distribution over strings. So we know that probabilities over all strings is now bounded by 1. Before we had, like for every string, we had a constraint that appending 0 and 1 bounds probability. Before we had semi-measure, the continuous semi-measure with infinitely many requirements. Here only one, so it's easier. Okay, and now we can say that machine U is better than machine V if all probabilities are bigger up to constant. So that's what's written here. And then there was a theorem, I've just deleted it. So that there is a machine that's better than all other machines. And it works like this. It first asks coin flips and asks curve fits until it gets a prefix-free description of some other machine. And so until it gets a 1 in odd position. And then it simulates the machine on, and whenever the simulated machine asks for coin flip, he takes it from itself. Okay, and so this is discrete a priori probability from optimal machine. So the notation is that M of X is equal to PU of X, where U is such optimal probabilistic machine without input. And now the claim is, our theorem is that K of X is equal to log binary logarithm as usual 1 over M of X. And so it will be the hardest theorem for the lecture. So we have to prove two inequalities, bigger than and greater than. So the question is, which inequality is easier? And I will tell you which inequality is easy. The equality that says that M is large. So this inequality is the easy one. Yeah, up to, yeah, all 1. Okay. So we want to prove this inequality. That means that we have to build one special machine without input. So, Okay, let's prove the easy inequality. Then I think we should do some exercises about this complexity to get used to it. Otherwise, it's a bit too abstract. But first, let us finish with this inequality. So how could the machine operate? We have a machine U prime here in our definition. And so there is a convention as usual. When it's true for all optimal machines, we drop the subscript. Okay, so what is so we need to come up with some special machine V for which this inequality is true if we replace M by PV. And so any ideas? So we just have the machine U prime, so we need to use it. It's the only thing we have. So what could we do with U prime? So we have access to random bits, and we have a machine U prime. So to prove there is not much what we can do. So we can ask for random bits, and we can run U prime. So answer is, let's run U prime on random bits. We have no other choice to get this proof. Okay. So then let us see what is probability of printing X. So what do we need to prove now? We need to prove that PV of X is bigger than 2 to the minus Kolmogorov complexity U prime of X. But it's true if we generate random coin flips and give it to machine U prime. So if this is equal to certain value K, then with probability 2 to the minus K, we guess precisely this program and machine V. And so machine V generate random flips, give it as program to U prime, and of course outputs the same string. I forgot to say it because it's kind of logical thing to do if we need to produce X. And so we have probability K to guess K random bits and give it to you. So we have proven this inequality. And so now we have proven that 2 to the power minus K is small. So when we take negative logarithm, we've proven that K is big, prefix complexity is big. So this inequality is proven. Okay, let's speak a little bit about properties of prefix complexity. Because now it's no longer true that prefix complexity is bounded by the length of the string. So remember previous lecture, we had T of X bounded by length of X plus of 1. But for K, it will not be true. Because now we need to make sure that our set of programs is prefix free. So we cannot have, for all strings, we cannot use the set of all strings as literal description. Identity, so we prove this using, for C, for plain complexity, we consider just identity decompressor. It copies input to output. So now for K, we cannot use this decompressor. We need to use prefix-free description of strings. So we can prove that K of X is bounded by length of X plus 2 log length of X. So how do we get this? Yeah, and prefix-free way. Indeed. Yeah, plus of 1, of course, because especially if there is no machine here. Yeah, so that's easy one. But we can do a little bit better. So there is another one. So we can have this plus A of length of X plus of 1. So can you see why this is true? Yeah. So what's the plan? We interpret, so we get first a program, we run universal machine on it, and then we get the length, and then we copy the next programs, and it's prefix free. So basically, because of this thing with sets S1 and S2 that I just saw. Okay, let me think. What else do we have? Or properties. And oh, so do you know about? Let's do something very useful for the other direction. So we have that if P is computable measure, then we have that K of X is smaller than. Okay, we need a so we need a family of computable measure. No, we don't need it. So this is bounded by logarithm of 1 over P of X plus O of 1. So, and then I don't know if you learned about compression. So if you have a measure, you can construct code words for decompressor. It's pretty important in computer science. And so, for example, there is Huffman code is very popular in practice, arithmetic coding. So you know how these things work? Yes. Okay. So we will, but here we have to be a little bit tricky. We will consider measures over infinitely many strings. And then Huffman code, there is a problem there because you start from smallest probability to build a dictionary. Arithmetic coding you can apply. But then there is, but we will use something else to get very tight bounds, and this is Kraft lemma. So Kraft lemma says, so if you have some numbers L1, L2, L3, and so on, then there exists a prefix-free set of codes with these lengths, if and only if sum 2 to the power minus LA is smaller than 1. So the sum over all A. So there is two versions. So there are two versions of the lemma. So the first one is if you take finitely many I. So I equal 1 till n. And this one is easy to prove. But let me write it first completely. So given L1 till L1, there exists P1 till Pn, prefix free. If and only if. Yeah, I should write nicer. If this condition holds. Okay, so the order is strange. So you need to write. So given a bunch of lengths, natural numbers, there exists a prefix-free set of same number with the code words equal to this length. If and only if this inequality is satisfied. Okay. L1, and so here I mean L1 is equal to length of Pn. Is this condition. Okay, so if we have finite set, how can you construct it? It's kind of greedy algorithm. So we sort the lengths, we make that they are sorted. So L1 is smallest one, L2, and so on, Ln. And then we assign the code words, just lexicographic first one that is free, and it will work. So why it works. So we don't need this. Or you can think about so here are all the strings that start with 0, here all the ones with 1. And then we have and so we assign the shortest one. So for example, it has 2 bits, then here lies the shortest program P1. So the shortest program we assign here, and all other programs, they have shorter lengths. So that means we can always put another program right next to. So if you do arithmetic coding, the hard part is that you need to find interval inside your given interval. But here it's easier because each time we look at a smaller interval. And so we can, so our probabilities are nice powers of 2. So so we put a code word here, and this might be like P2, and so on. And we can have P3 and P4 maybe of the same length. And each time so it's clear what I mean with this block. That's just P1 is equal to 2 zeros. So when I go here, so here is 0, here is 1. Here is 0, 0, 0, 1, 1, 0, 1, 1. So there is binary 3. And the width of the block is 2 to the power minus the length of the string. And so we can view this as real numbers between 0 and 1. So that's the scheme I'm building. And so each time we look to the smallest string that's available, that's still free and has the appropriate length. And so we put the blocks on top of each other. And the inequality guarantees that we stay in the unit interval. So we allocate all our programs by the code. So this is a clear thing. Okay. So now we have to do something more complicated. We have to do everything in a computable way. And if we have an infinite sequence of numbers, then we need to get them sorted. But we cannot get the computable infinite sorted way, because there is some computational process that can say very far up, the probability goes up. If we have this with equality, then we can sort them. Because we can make sure that when we get a number, we can wait until we know for sure that all subsequent numbers are smaller. But we will have semi-measures, and we all have inequality all the time. So we cannot sort them. And so then there's a Kraft lemma. Oh, by the way, I only proved one direction. So I said that if I have the numbers, then there are strings. Okay, so just the complication for infinitely many, I will prove in a second. Let's first see why the other direction is true. So if the claim is that if these prefix-free words exist, then the sum is bounded by 1. So why is it happening? So when we have so when we have prefix-free words, we can put them in this scheme here, right? So I write all the words in this table, and the width of the given word is 2 to the minus length of this word. So if the set is prefix-free, that means if I write them in the table, the blocks will never overlap. The only way for 2 blocks to overlap is if the smaller one is a prefix of the longer one. So if I put everything on top of each other, if they're prefix-free, it means they all fit in my block of unit length. And this inequality must be true. So there are some gaps if and only if it's strictly smaller than 1. by the way, I also had very difficult week. And then I completely crashed. And then, so I went to bed at 8 or 9, somewhere between 8 and 9, I fell asleep. And then at 1, I was awake and then so like completely nervous. So I took sleeping pill. But then I slept till 10 in the morning. But then I didn't have much time to prepare this lecture. But I feel opposite from you now, because each one of you is like, it's okay. I completely understand. It's yeah. It's
I want to ask you about
yeah.
the history of this lemma because it is also known as Kraft Macmillan.
Yeah. I also seen this. Yeah,
And I saw somebody call this just Macmillan. I call it so. It's really interesting who invented this lemma.
yeah. Well, I disagree if it's that interesting. I mean, there are simple things that have 500 names. If it's easy, I don't care who invented it. If I think, okay, I can invent this myself too, then I'm not. Yeah, I didn't check the history. Okay, so yes. So I moved other direction. And now we need stronger version, not for finitely many, but for infinitely many ones. And we need, so we need something stronger. So it's called not Kraft, but or Macmillan, Kraft Macmillan, Chaitin make that the extension. So he also one of the inventors of Kolmogorov complexity. Kraft Macmillan Chaitin. He considered this, but computable. And he wants a computable sequence of prefix-free code. And I already explained what is prefix-free and computable. That means that the mapping I to the ith code word can be evaluated by computable function. Okay, but now we need some clever idea to do this, because sorting doesn't work. And the plan is to maintain a set of code words, a finite set of code words that's still available. At any moment, our set will be finite, and every code word will have different length. This is our invariant. So initially, it will be only one code word, the empty string. So maintain and maintain finite set. One, two, and how will we call it again? Of different length. And so our algorithm will ask for the next length and then assign a code word right away. And it will do in kind of greedy way. So it will look if it has a code word already available of the length that it receives. So when it gets L, it outputs code word of length L if it exists. If it doesn't exist, then it will look to the shortest code word, to the longest code word that is shorter. So he needs to allocate, in our table, he needs to allocate a code word. But if this length is not available, he needs to destroy a bigger interval. So note that this is a very tight condition. So when we are very close to 1, we cannot waste any space. So we will break the smallest block that is big enough for assigning a code word. And then we will create new code words. But when we break a block, so imagine that the whole one block is available, we will add new words. So imagine that all available F, so we need to we need a string of length 3, for example. But here, all the free has length 4 or more. So the only free space here is of length 4 or more. And we need to assign a block of length 3, but we still have the whole one block available. So then we will assign this block to the new string that arrives, and we will add the new blocks to the set of free strings. So this will be free, this will be free, and that's it. But we can do it in any way. So when we need to break a block, we go to the shortest string, the longest string that's shorter. And then we create blocks whose length are 1 longer, 2 longer, 3 longer, and so on, until the length of our block that we need to assign. And so we keep our invariant. The new blocks that are created did not exist before. A invariant, all of the free blocks have different lengths. It was our invariant. And we keep it. And then we are guaranteed that this always works. So, okay, now we need to understand why it always works. It will never happen that there is a request for a block that is bigger than our smallest width. And so we will never add a term here. And so know that each time there comes a request here. And the largest possible request will always correspond for every future request. There will always be a code word that is short enough. And why this happens is because all the lengths are different. So the free space is precisely equal to our current sum, 1 minus our current sum, the measure, because each time we assign a block, so each time the sum increases while scanning the else, we assign a block and the free space decreases in the same way. So so that means that in each request we are still below 1 or at bounded by 1. So that means that when we ask for a block, so so it's clear, right? So when we so what happens if there is what needs to happen for not having a long block, a block long enough? So what is so imagine that we ask for a block of length 2 to the power minus, so we need to assign this block of length 5, and there are no blocks of length 5 available or shorter. It means that in the worst case we have a block of length 6 plus a block of length 7 plus and so on. We get so we get a finite amount of free blocks. At any moment, the free blocks are finite. And so when all our free blocks start from 6 and include everything, we can never make a request of length 5 or less, because it would violate the sum constraint. Okay, so now we have this lemma. And now we can prove this theorem. So if P is computable, then, so computable measure, that means sum over the strings, is at most 1. Computable, well, measure or semi-measure, then it's only easier. Okay, so if P is computable measure, then what when we do? We can create the else for x by rounding. And so we round P of x, we round it down to the biggest power of 2 smaller than P of x. And then by this lemma, we get the code word. So the program of X will be the code word. And so we have a probability here. Okay. Now let us do, so this is, so is the proof okay? Should have for some, it's okay. Yeah, it looks like, okay. So now let's make the theorem a little bit harder. And then we have the other inequality. So if P is lower semi-computable, semi-measure, then the same thing is true. So if P is lower semi-computable, same measure, then the same thing is true. So we can actually construct a special decompressor for which we have a more precise bound. This one. So how it works? No, we need a bit more. It's not so important. Okay. So the plan is that each time P of X, so now P of X is lower semi-computable, we approximate from below. Before we said, let's look to the smallest, the biggest power smaller than P of X. Since P of X converges, this converges too. Now we do precisely the same thing. But when P of X increases to, and surpasses the next power of 2, reaches the next power of 2, then we ask for a new code word, but one bit shorter. So this is the plan. So when we discover, let's remove this. So when P of X bigger than 2 to the minus K, request a new code word. So if we ask for I minus 1 code word, we ask for I'd code word, and we set the length equal to K plus 1. We set it a little bit more. And I set it a little bit more to satisfy this condition on the length. Because for a given X, when it was a little bit lower, we already requested the code word. So the moment this surpasses 2 minus K, we already asked for a code word of length K minus 1. So that's why we have to ask for a little bit longer K code word, because the probability appears several times in here. And so for a given X, we will ask code words of length. So if P of X is a final value, then we might have asked code words for P of X divided by 2, P of X divided by 4, and so on. That's why I ask an extra bit, so that the sum of all the requests, and so for the same X, when we discover that P of X gets larger, we ask again for a code word. So for the same X, we ask for many code words. But then we have to look to this bound on the L's. And this is the plan. So the contribution of 2 to the power minus Li is now equal to 2 to the Li will now be half of P of X here. And half of this value here and half of this value here. So that when we add up all the Li's for a given code word X, we have at most P of X here. Okay, let me repeat. I think the problem is with the algorithm. So what do we do to get the code words for the decompressor? We need to construct decompressor. It means we need to get a set of prefix-free code words. And then we need to say what is the output of the code word. And so we will ask algorithm and the lemma for code words. We just have to tell what is the next I. So we give this algorithm, we get the code word. And we need to just to make sure that this condition is satisfied, otherwise this algorithm might fail. That's the only thing we have to do. And so what we do is we will evaluate P of X in parallel for all the strings. And then as time progresses, we will find bigger and bigger values of P. And so each time some value increases a power of 2, steps over a power of 2, we make a request for a new code word for this X. What does it mean when we make a request? So the lemma gives us a code word, and then decompressor says, oh, when I get this code word, I need to output X. So when we discover X passes power of 2, decompressor asks for a code word. So that's a process he always runs when he receives a code word. He starts to run. So I need to, okay, I understand where is confusion. So I need to construct decompressor. And so decompressor receives a word that he needs to decompress. And at first he will not look to this word. He will just start a process that's the same regardless of every input word. And that is, he will run this algorithm for different else. And he gets the else by, in parallel, increasing, computing all the probabilities from below. And in this process, he receives code words L1 and so on, and he gets the sequence of code word. And that he compares this code word with its input. And when he sees it's the same, he knows what to output. So because X is requested, if a certain X requests a new code word and it's precisely the code word of the input, he knows X is the corresponding code word. So that's connection between the lemma and the coding theorem. So that's how we get this thing here. So there are two factors too here. So one comes from the +1 here, and the second from the rounding of P of X. So it can happen that P of X grow, but it just didn't reach the power of 2. Then P of X is another factor smaller than the length of the code word it requested. Okay, so this is the proof. So that's how decompressor DP is constructed. It's the hardest theorem of the lecture, so we can repeat once more. So we have to believe two things. First, the lemma. We need to prove the lemma. And then the harder part is to see why the lemma gives us the decompressor. And so decompressor is just, that's a better way to say. Decompressor is just a list of pairs. And so whenever we have a list of pairs, P1, X1, and so on, we can define a decompressor. And if the pair of first elements is the set of first elements is prefix free, then compressor is the prefix free. And just a function is just a list of input-output pairs. And we need the decompressor to be partial computable. That means that this list just needs to be computable. That's the thing. And so then the question is, where do we get the list of P1, X1, P2, X2, and so on? And this is from the lemma. And so the x's we get by approximating from below, and each time one crosses a power of 2, we ask for code words P from the lemma. Okay, and then we have to check carefully that this is satisfied. That's why we were fiddling with this +1 here. Okay, so that's also, if this proof is clear, it's major achievement of the lecture. And now let us prove symmetry of information. So Leonid Levin is a guy from P versus NP problem, and when he was a student, I think 16 or something, Kolmogorov gave a lecture about his theory, and he said that in Shannon entropy there is symmetry of information, and he wants it in his theory too, but it needs to be with O(1) precision. And he said that he didn't know how to do it. And then a few days later, Levin came to Kolmogorov and he said, here is a precise version, but your definition doesn't work. We need prefix-free complexity. And so let me write what is this version of prefix. So, and there is a little particular thing here. So we say that complexity in a string plus complexity in another string. Oh, I need to define conditional complexity. Given x and k of x is equal to k of xy plus O(1). So this was Levin's answer. Then something funny happened. So Kolmogorov ran away. He said, I have no time. He kept saying this for more than a month. I don't know the precise amount. And then finally, Levin managed to have a phone call with Kolmogorov. And Kolmogorov said, yeah, yesterday I found it myself. Which is maximally demotivating. But Kolmogorov took Levin as PhD student. So it's kind of, yeah. But now this is called Levin theorem. So Kolmogorov was nice about it, but maybe he wanted to find the proof himself without listening to, I don't know, but I mean, it's easy to believe that he was very busy because all these PhD students and yeah, and then crazy things he had to with authorities. Okay, yes, so yeah, but before I have to define conditional Kolmogorov complexity. And there is like a common mistake that in published papers happens. So we have to be careful with this. So here is our definition, and you can guess, so complexity of x given y is maximal length of a program that on input y produces x. So nothing changes here, but what about prefix condition? That's the dangerous part. Okay? So the rule is that for every y, for every condition, the set of programs P must be prefix-free. But if I change y, I can have another prefix-free set of programs. So that's the rule. So examples, kx given x is equal to O(1). K of x given length of x is bounded by n plus O(1). Note that before it wasn't possible. Sorry, without n in the condition, we don't have that it's bounded by length of, so here, n is the length of x. It wasn't possible. So it was not true that complexity of x is bounded by length of x. And thanks to this theorem, we can even understand why it's not true. Because if imagine complexity was bounded by length of x prefix complexity, then let us look 2 to the power minus complexity. It needs to sum up to at most a constant. Okay? So we so imagine that k of x smaller than n, it means that m of x smaller up to constant factor 2 to the minus n because of our main theorem. But now let us sum over all n and sum over all x of length n. Length of x equal n. So we have 2 to the power minus n here. So here we have m of x. M of x. And so we know that it is when this is true, and we have sum over n of 1. And so it's infinite. So we can understand that complexity is not bounded by n. So we can try to make another bound. So can we have that this is true? And so we had an upper bound for 2 log n plus constant. We proved the upper bound, I wrote it. Can we have 1 log n plus constant? And then what we get here, m of x is bigger than 2 to the n minus log n. And so what we get here is m over x. Here we have, so this is replaced by this value here. When we multiply by 2 to the power n, what is left is 2 to the power minus log n. So this is 1 over n. And it's divergent, still divergent, very slowly divergent, but we understand this doesn't work. Okay, so let's try next one. Log n. So what you think will happen now? Convergent, or who votes convergent? No? Divergent or convergent? Yeah, you're right. And so what will we have here? Yeah. If we put 2, yeah, you got it. Yeah. So if we have log n minus log n. So what's happening here? Well, yeah, then we just sum over the bit size of n. So then we write another sum, like sum over k, and then all k is equal to log n, and then we will have the same thing. And so 2 to the minus log k, and it's indeed divergent, and it can be repeated. So as soon as we drop a 2 somewhere, we are good. As soon as we have 2 log k here, then it is 1 over k squared is converging. Or instead of 2, 1 plus epsilon log n, log n would also work. Okay. Yeah. Symmetry of okay, and here you can see, to get this result, we need for every n a different set of prefix-free programs to get this result. And because we need 2 to the n prefix-free programs of length n plus O of 1 plus a constant. So this O of 1 doesn't depend on n, but only on the machine. So we cannot have the same. Okay. So this is important for every y. Now 0, 1 star, 0, 1 star. Prefix-free machine if okay. So for every y here. Okay, and then we have the usual examples. So so if f is computable, then we have k f of xy given y smaller than k of x given y plus O of 1, and O of 1 depends on the function f. Clear? something similar in the condition. K and X given Y smaller than K X given F of Y. Okay, it's easy, it's too boring, right? Okay, now I need to tell the proof here. It's our next task. And then we speak about expected value of entropy. What's the time? Oh, we are late already. Okay, there are no exercises about entropy. We can do it later as well. So, and the proof is tricky. So the plan is to work with semi-measures. So we will use coding theorem. Okay, one direction is easy. So which direction is easy? So before we use coding theorem, we will first prove easy direction. That's for the hard direction. I almost forgot to tell the easy one. Yeah, sum is greater. That's the easy one. So we will just concatenate the two programs. But so this is produced by program P, this by program Q. But there is a subtle detail now. We concatenate the programs. And now our decompressor we construct here needs to split the programs. And so what will it try? It will try all the prefixes of the concatenation. And by prefix property, it knows that it will only on one prefix it will halt. And after it halt, it knows the prefix, so it knows P. So it can, well, when it halt, it knows X. And then it can start to run Q. And K of X will be precisely the length of P. So that will go here. And so we have proven this inequality for our special machine. And so we switch with O of 1. Okay, but now we have to prove other inequality. This one. And we will prove it using measures. So I will translate everything to measures. So we defined M of X here. Well, let me first reorganize things. So let's put K of X to the other side. So this one you already know. Well, so let us subtract minus K of X plus O of 1, and then replace everything with measures. So we need to prove that M of Y given X of K of X. So I will leave this K of 1 will remain is bigger than M of XY divided by M of X. So that we will prove this inequality. So now there is a little problem. So imagine that it's not true, but imagine that this was lower semi-computable. Then we are finished. Well, almost finished. We just have to prove some condition of oh yeah, but I didn't define conditional a priori probability. But I think you can guess the definition, right? So so how it was defined? It's just machine with no input that can ask for random coins and a prints X. But now we allow the machine to have input. And again, we can have a biggest machine up to constant factor, the same story here. And so this is defined by a best machine. And so we just have to construct one machine and we are good. Oh, but there is third definition of Kolmogorov complexity. We actually don't need a machine. We only need a semi-measure, and it should be lower semi-computable. So remember in the definition of M of X, or just when we have machine without input V, and we have PV of X. We already said that when we sum over X, we have at most one because it's defined by probability. Second is this measure is lower semi-computable. Why? So how can we approximate this probability from below? Yeah, we can compute on all the randomness, and each time certain randomness improves, produces X, we improve the estimate from below. So we add something to the current estimate. Each time we find random coins that give a P of X. So PV of X, lower semi-computable. Now the opposite is true. When we have semi-measure and it's lower semi-computable, we can build a machine, PV of X. So what I want, yeah, okay, I think this is a nice exercise. So let's think about it. So if we can approximate PV of X from below, we can build a machine. So how will we build a machine? So we just have to think about the property. So when we sum over all X, we will get something smaller than 1. So we can just consider unit interval between 0 and 1. So each time some probability improves, we look to this improvement and we allocate some intervals. And now our job is even easier because intervals that are allocated don't need to be like one segment. We can have many little segments to build the machine. And so we then check whether, so the machine gets random coins, views it as a real number, and then check if this real number is in one of the allocated intervals. And so machine keeps asking random coins until it understands that its infinite sequence is inside one of allocated intervals. And so you build a machine in the other way. And so what have we proven now? We have given a new definition of Kolmogorov complexity, well, of a priori probability. It's the largest lower semi-computable semi-measure up to constant factor. Because for every lower semi-computable measure, we have a machine that gives bigger measure. And it was defined as the measure of the best machine. So we understand that the best machine will be bigger than any lower semi-computable semi-measure. But also the best machine itself produces lower semi-computable semi-measure. So that's why it started 3 definitions. So next lecture, there will be information distance. There is some abstract question, and we want to find mathematical notion. And how people invented it, it was to see, oh, we have 3 definitions of complexity. We will get, again, 3 definitions, and it nicely works. So, but that's next lecture. So this is why it's nice to have, in physics also works like this. The people think about the model, and they take all the properties that feel fundamental, they list them, all of them. And then when they look to the invisible model, they try to find one that also has the same property, as many as possible of the same properties. But sometimes it doesn't work. You need to drop some principles. But the preference is the one with the most principles respect. Okay. Yeah, we have to prove this thing here. So now we use 3rd definition. We will construct lower semi-computable semi-measure to get this inequality. So here our problem. So first thing, let us understand that first thing that I will prove is that this is semi-measure. Problem will be with lower semi-computability. So how do we see that this is semi-measure? We will write this, we will prove that this is bounded by sum over y of mxy. So up to constant factor. So why is it true? Why, if I sum over second argument? Oh, yeah, so by the way, do you understand what is this? I think it's easy to guess also. So we defined semi-measure for one argument. We can define it for two arguments just by coding the pair into one string and apply this definition. Or, yeah, we can have a machine that prints two strings separated by blank. If you want, it's the same definition. But usually people pair up. Okay, now we understand what is this. And the claim is that if we sum over y, we have at most this thing. And so we can prove this with our third definition. Why? Okay, so we don't know this. What happens if we sum over x here as well? We will get something bounded by 1. So with the sum over y, we have semi-measure. So when I say that Q is semi-measure. When we sum over x, we get something bounded by 1. Now I claim that Q is Lauer semi-computable. Why? This one is Lauer semi-computable, and we take a sum. So we can Lauer semi-compute by approximate each term for t steps and summing t steps. When we increase t, it will get bigger and bigger, and eventually we will reach the limit. So this is Lauer semi-computable. So Q is Lauer semi-computable semi-measure. And so we conclude that, also this was definition. And so we conclude that it is bounded by m of x up to constant factor. Because, sorry, other direction. Because m of x is the largest one. And so m of x is bigger up to constant factor because it's bigger than every Lauer semi-computable semi-measure. Okay, so here is m of x. So what have we proven now? When we look to the right-hand side, we have proven that this is a semi-measure. But it's a ratio of two Lauer semi-computable things. So it's only limit computable, not Lauer semi-computable. We need to deal with this. And so the solution is a very weird trick. So solution will be to multiply this. Okay, now I will create an extra parameter. I will pretend I don't know Kolmogorov complexity, and I will call it some generic name. Okay, let us not forget which direction we are proving. So we want to prove this direction. And here I will use parameter k. And here I will make some space. And so I will say that this is equal to the maximum of 2 to the power k tilde. And we need 2 to the power k tilde equal to the minimum of 2 to the power k and 1 over m of x. So this is pretty weird thing. But first, let us check we understand what is written. So we have mxy, 2 to the power k tilde, and k tilde is the minimum of two things. So definition is clear. Now let us try to understand that this is Lauer semi-computable. Oh, this is a problem. So m of x is Lauer, so it becomes big. Oops. This doesn't work. So let's try this. Yeah. Hopefully this works. And so it's the maximum of k. Yeah, I think this works. So the question is this definite? So let's take another name. Of course, you understand what will be my plan. We need an equality, so I will. And so we need to prove that this is small, so we need to prove that Q is big when we set K equal to Kolmogorov of complexity. Okay, but first let us try to understand that Q is Lauer semi-computable. So this is clearly Lauer semi-computable. M is Lauer semi-computable, so this is so M gets bigger.
So 1/m.
Yeah, 1/m is. So it doesn't, oh, my fix doesn't work. Yeah. Looks like I need to do something with 2 to the power. I'm confused, neither with max or minute works.
Why do we need the first one? It's like the tilting the line.
Yeah, that's a good point. We don't need it. Right. Yeah, I thought when I was preparing, I thought it was a bit too easy. Start to see why now. And okay, we need to, let's try sum over K tilde. And we want K tilde, to be smaller than K. And we want this thing to be smaller than 2 to the power minus K tilde should be bigger than M over X. Well, if I completely screw, then I cannot ask it on the exam, but it would be sad. Okay. 2 to the power minus K smaller than M of X. Something like this they're using. Okay, tilde. So they say that it's equal to 2 to the power minus K. No, that's a different one. Okay, K. Proof of last part will be a next lecture because unfortunately we are running over time already. It's
Make a 10-minute break.
yeah, but I'm afraid like the proof was really long and I wrote the proof. I prepared myself on the board and then I must have missed in lower and upper semi-computability because I say, oh, my proof is shorter, I'm clever. But usually, if I think I'm clever, the punishment is a bit later, like in now. But yeah, it's almost 8, so it's too much of lecture anyway. So next lecture, I will start with finishing the proof. And but you already know a big part, so this is clearly part of the proof of any proof that is vaguely in my memory. But short proof doesn't work, so yeah. So let's have 10 minutes break and then we will solve some exercises.